Okay, good morning, everyone. In today's lecture, we'll be looking at the magnetic flux, Faraday's law, Lenz's law, and the induced electromotive force, and we'll be solving a few examples. So the magnetic flux is not different than what we have seen earlier when we calculated the electric flux. The same concept. The phi here, B for the magnetic flux, is indeed the dot product between the magnetic flux and the area vector for this loop that the magnetic field is going through. Now, the result of the magnetic flux is the scalar product or the magnitude of the A, B times the cosine theta, where theta here is the angle between the normal unit vector on this area given by this. So this is the area vector. Here, the normal unit vector is normal on this area and the magnetic field. So the angle theta is between area vector and the magnetic field, given by AB cosine theta, where phi b is a scalar quantity. Now, Faraday's law says that there will be an induced electromotive force, basically proportional to the flux variation, the time rate of the flux, of course, with the sign minus here that we will talk about in Lenz's law. So it is the minus d phi over dt, where d phi over dt is the time rate of the flux. Again, the flux is the dot product between the magnetic field and the area vector. So looking here at the electromotive force, epsilon equals to minus d phi over dt. Now distributing this derivative on those two vectors is going to give me dA over dt dot b plus a dot dB over dt. So I have here two types of electromotive forces. Sources, I would say the one of them is called the motional electromotive force, which is basically due to the variation in the loop effective area within the magnetic field. And the second one is time varying magnetic field. And this one we call it transformer electromotive force. Now let's go back to this sign, try to understand where did the sign come from. So we know now that the electromotive force is proportional to the variation of the flux in time. Lenz's law, however, this negative sign is the following. Lenz's law states that the induced electromotive force in a loop due to a change in the flux, as we have seen, is the result of the opposing magnetic field that is trying to oppose the change in the flux. So if you have a flux that is increasing, the opposing magnetic field in the loop will go toward decreasing this flux, and the current is based on the right hand rule for this opposing field. Now, if you want to look at this one uh, here in more detail to understand what's happening, if we have this magnet, for example, that you can see based on the velocity is going further away from the loop, this means that the magnetic field or the flux in this loop is decreasing. If the flux in this loop is decreasing, we will use the direction of the magnetic field as our positive direction. If the flux is decreasing, then we will put our thumb in the direction of the magnetic field, and then the current will be the directions of the curling fingers. So if the magnetic field is decreasing, the thumb for the opposing magnetic field will be in the same direction of the field, and then the right and the fingers will give me the direction of the of the current. Now, if the magnetic field is increasing, Again, the direction of the magnetic field is our positive direction. Then I will put my thumb in the opposite direction to the magnetic field, and then the fingers, the curling fingers, will give me the direction of the current. We will see this in more examples. Okay, so let's look now at this example. In this example, we have this loop that is made with this bar here. The question reads the following. The circuit shown below consists of a 3 volt, 1.5 watt light bulb connected with ideal wires with no resistance. Conducting bar with no resistance is connected to the wires and is pulled to the right at a velocity v through a uniform magnetic field B of zero point 0.1 Tesla into the page, where W is 10 centimeters and L here is the length. What speed V must the conducting bar have to light the bulb to full brightness? So in this case, I will redraw here. I have my circuit as the following. So there's a light bulb here. I have the bar here, and the velocity is in this direction. I have the magnetic field, uniform magnetic field, pointing into the page. Okay. Then I have the magnetic field as point 0.1 Tesla. I will take my coordinates to be X, Y, and Z, like this. I have this light bulb, 3 volts. So I'll put the electromotive force here as 3 volts, and the power at 3 volts it will give me a power of 1.5 watts. I need now to calculate the velocity that will give me a full brightness. Now the length here is L, and width is W. I know my magnetic field B is zero point 0.1 pointing into the page, which means it's minus k hat. I know the area here is a k hat pointing out of the page. Then my epsilon here is minus d phi b over dt. Epsilon is minus d over dt for b dot a, or epsilon equals 2 minus d over dt. B is 0.1 minus k hat dot A is WL k hat. Then epsilon is, now if you take the dot product between the B and the A, k hat minus dot k hat is going to give me minus 1. So here I have, and 0.1 will go outside, so I have 0.1, and also the W will go outside for 0.1 W d over dt L. So epsilon is zero point 0.1 times 10 centimeters, which is zero point 0.1. dl over dt is v, so v is epsilon 3 divided by 0.01, which means v equals to 300 meter per second. So this is A. B, calculate the opposing force resulting from this velocity. Okay, so now we will go and apply the Lenz's law in order to find the direction of my induced current. Now, I have the magnetic field pointing into the page. With this bar moving to the right, the flux would be increasing. If the flux is increasing and my magnetic field is the direction of the magnetic field is my positive direction, then I will be pointing my thumb in the opposite direction of the magnetic field, and then my finger is going to give me the direction of the current. And in this case, I can see that the current is going counterclockwise. The current going counterclockwise this way, and applying the right hand rule, I can see that the opposing force is pointing in this direction. And now I need to calculate this. So this is the FB, the magnetic force. And I know that FB equals to IL cross B. So here my L is going in the J hat, and my B is in the minus K hat. So FB is I, we said that the L here is the W, J hat, cross point 1, which is, I'll put it now as the B minus K hat. I know that the power is the electromotive force times the current, which means that the current is 1.5 divided by 3. So the current equals to 0.5 ampere. Then W is 10 centimeters. So I have here FB equals to zero point 0.5 times 10 centimeters times 0.1. And now J hat cross K hat is I hat. However, here I have minus, then it will be minus I hat. So this one is minus I hat, and this is expected to be in this direction, opposing the applied force. Then FB is 5 10 to the power minus 3 minus I hat Newton. Now, what is the applied force? If V is constant, then the applied force when V is constant is minus FB, which means that If applied equals to 5 10 to the power minus 3 I hat Newton. In this question, we have the applied force in the same direction as the velocity, and we have the FB as the opposing force. Now, the power is P due to this applied force. Now, imagine that this force is increased so that the constant speed of the bar is doubled. The speed is doubled. Under these conditions, what are the new force and the new power induced? So, in this case, let's look at the equation for the electromotive force that we have derived earlier. Epsilon equals to VW times B. So if the velocity has increased, was doubled, then the electromotive force would also be doubled. If the electromotive force is doubled, then the current is doubled. If the current is doubled, then the force is doubled. So I have either A or B so far. Now, if the current is doubled and then it's squared, then the power would be 4 times the old power, which means the answer V is the correct one in this case. Now, in this question, in which of the following situations is a current induced due to a motional electromotive force? We know that the current induced here in A is a motional electromotive force because I have this bar moving basically and the magnetic field is uniform. So I have an induced electromotive force here. In C, also I have the magnetic field as uniform, and this loop is rotating, causing an induced electromotive force. So it is an electromotive force. I have a current induced here. In B, although this loop is moving in this direction, however, I don't have any variation in the flux. The flux is constant always, no variation in the flux. So there is no induced current in this case. In case D as well, I have this loop that is moving along the wire, which means that the magnetic flux is not changing because the magnetic field is not changing in this case. So I don't have an induced or motional electromotive force. So only A and C are giving me motional electromotive force. B and D are not inducing any current. Now let's look at this question. In this question, we have a circular loop of wire falling toward a wire carrying a current going to the left. What is the direction of the induced current in the loop of this wire? So here we have the following. We have a current in this wire going this way, and we have this loop, and this loop is falling in this direction. Now, based on the right hand rule, the magnetic field in this case would be into the page above the wire and would be out of the page below the wire. Now, when this one is falling in this direction, the magnetic field is pointing into the page, and the magnetic field, the flux would be increasing, pointing into the page because it is coming closer to the wire. So since it is increasing into the page, Remember, we said that the direction of the magnetic field is the positive direction, and since it's increasing, my thumb will be pointing in the opposite direction, and now my current is based on the fingers of the right hand rule is going into this direction. Now, once this wire falls and becomes now here and going further down, then in this case, the magnetic field is pointing out of the page. However, the magnetic field will be decreasing in this loop. So if the magnetic field is decreasing, then we will put our thumb in the direction of the magnetic field, and my fingers will point toward the current. So the current is still going in the same direction, counterclockwise, and the answer to this question would be B. Okay, so in this question, consider a loop rotating in a uniform magnetic field B with an angular velocity omega. What is the induced electromotive force in this loop? Now, remember the electromotive force is given by minus d phi over dt. Now, since the motion here is, as you can see, this rotational motion is defined by cosine theta, then my phi, that is the dot product between the magnetic field and this area, would be BA cosine theta. Since it's a rotational motion, then BA cosine theta. Now, BA cosine theta, the area is constant, the B is uniform, then I would be applying my derivative here to cosine theta, which basically theta is omega t, the angular frequency times the time. So in this case, the derivative of cosine omega theta is going to give me BA omega sine omega theta, and the minus will cancel with the minus. So the answer to this is this expression. The electromotive force equals to the magnetic field times the area times the angular frequency times sine omega t. Now let's apply this on our example here. We have a coil with area 2 meters squared, rotates in a 9 to the power minus 3 Tesla magnetic field at a frequency of 60 hertz. How many turns are needed to generate a peak voltage of 170 volt? So in order to solve for this problem, we will again use the expression we just introduced, which is electromotive force for those angular rotating coils as given by, now I have a loop more than one turn, that's why I will put n here, so it is B A omega sine omega t. In order to calculate angular frequency, it's 2 pi f, where f is 60 hertz in this case. And this equals to 377 radians per second. So I know the magnetic field B is 9 to the power minus 3 Tesla, I know the area is 2 meters squared. I don't know the number of turns. I know the electromotive force being 170 volts. However, it says here as a peak, which means that my coil is gonna go uh, from zero flux into the maximum flux. And in this case, if you go back to here, when you go from zero flux is when you have this coil here parallel with the magnetic field. So the coil is like this. This is where you have the zero flux, and then you have maximum flux when the coil becomes perpendicular on the magnetic field. Maybe minus 90 degrees to zero. This is going to give me a maximum, a peak. So in this case, my sine omega t will take the value of 1, which basically is going to give me the maximum peak. So if sine omega t varies from 0 to 1, I get the maximum or the peak voltage. So here I will put epsilon with 170 degrees. So back to my expression here. I have 170 degrees equals to, I don't know, n times 9 to the power minus 3 times 2 times 377 times 1. This is going to give me the maximum electromotive force. Then n equals to 170 divided by n equals to 25 turns.